Welcome. I'm Alexander Rose, the director of the Long Now Foundation. Normally we do a thing called a long short, or a short movie that exemplifies long-term thinking. But since in the last 2 weeks, we've been working with News Trust and Kirk Citron, who's been running our project, or a project with us, called Long News, news that matters over a long period of time. We thought we'd have them do a quick presentation. The last 2 weeks has been a news hunt on the future of energy, and I'll have them give you a brief on what Long News is and News Trust and how we've been working together, and then we'll pass it over to Ed. Thank you.
Good evening. I'm Kirk Citron, and I'm an associate and an editor at the Long Now Foundation. And this is Fabrice Florin, Executive Director of News Trust, and we're going to briefly tell you about this week's energy news hunt. But first, some background. We've been running a project called The Long News, which, as Alexander said, looks for news stories that might still matter 50 or 100 or 10,000 years from now. And just to give you an idea of a couple of themes of the kinds of things we've been looking at over the last couple of months, there's talk that there may be another mass extinction event. But the problem this time isn't an asteroid or a volcanic eruption, it's us. And we found headlines like more than 800 wildlife species are now extinct, and maybe a reason we should care, which is that animal biodiversity keeps people healthy. A second area, another theme, is the extension of human lifespans with stories like it's starting to get crowded in the 100 years olds club, and half of US babies living today may reach 100. So that's a flavor of the kinds of news stories that we're looking for that might have some kind of long-term significance. And lately, for obvious reasons, we've been thinking about the future of energy, kind of hoping that the current crisis will prompt a deeper conversation about the need to find alternatives to oil, like fusion, which we're going to be hearing about tonight. And so to do that, we've partnered with News Trust to do this energy news hunt, and I will turn it over to Fabrice now to tell you more about that.
Thank you, Kirk. News Trust is a community of citizens that care about good journalism because we need it to make informed decisions as citizens. And so we rate the news for quality, and we feature some of the best stories that we find every day on our site. And we offer a hybrid news filter, which engages professionals, amateurs, and computers to filter the news. And this holy trinity and collaborative approach is an effective way to find good journalism all in one place. And it manifests itself on the homepage of our site, newstrust.net. Every day our editors feature stories worth reading on topics like, in this case, the future of energy. But you can also see our reviewers at the bottom of the screen, and they're doing the reviewing, which helps us feature the day's top stories based on their reviews and ratings. And those are filtered by computer algorithms. So this week we're hosting an energy news hunt, and we hope that you will join us. It works a little bit like a scavenger hunt. We're all looking for good journalism about the future of energy. So each day our editors post stories on our site, and we invite you to review them. When you click a story on our site, you go to the news provider's website, and you can see our review form in the top right corner. And what we ask you to do is read the story, then click on the buttons that describe it best. Is it factual? Is it fair? Is it well-sourced? We have other criteria. And based on your answers, we're able to surface some of the more interesting stories. So what kind of stories have we been finding? Past week, we looked at stories about solar. We found some great articles from Der Spiegel and Climate Biz, again, mainstream sources, independent sources. We've looked at nuclear power with stories like these, the case for and against nuclear power from the Wall Street Journal, and great insights from other publications like Spiked. As far as wind power, again, interesting stories from UPI, Popular Science, and many more. And the topic of today's talk, fusion energy. Again, the coverage ranges from the BBC to the New Scientist. And it's the diversity of all these sources that really makes it interesting, that we can actually see how the different sources cover the same topics. And we've reviewed hundreds of stories already. Next week we'll share the best and worst coverage on both the News Trust and the Long Now blogs. And we'll keep adding stories on our site. So we hope you'll join us, and the best way for you to do that is to go to newstrust.longnow.org, and we hope to see you online. Thank you very much.
Thanks. Thanks, Fabrice. I'm Stuart Brand. There's a little continuity here. Fabrice Florin was at the Hackers Conference in 1983 and made a video of it that's still available online. This is an event that Kevin Kelly and my wife Ryan Phelan and I organized back in basically the Bronze Age of computerdom. And what's interesting is you'll see people there like Richard Stallman and others who were young pioneers at the time are all still very active. But the stuff you see them playing with looks like a Schwalian hand axe kind of level of technology. What's going on across the bay and over the hill at Livermore is a search inside star power. Stars are powered by fusion, and we've been looking for productive ways to bring that power here. And Alexander Rose and I went to the National Ignition Facility a couple months ago, and it knocked our socks off. Basically, everybody who sees that goes, oh my God, one, this is amazing anyhow, to do that massive kind of stuff with lasers, but it might mean very good things. So we can't all go to the National Ignition Facility, so what Alexander and I decided is maybe we could bring the National Ignition Facility here, and in the person of Ed Moses and his presentation, here it is. Ed?
Thank you so much to invite me here, and all of you for coming out. I'm going to be talking about laser fusion energy and what that means and the future of it. And it's going to be at the story of the National Ignition Facility. And that is actually a picture of the National Ignition Facility transported to San Francisco. Now, when I go around the world, I transport it to Tokyo or Paris or wherever I have to be, and that's, or happen to be, and that's sort of the point. My purpose is to show you, by the end of the day, by the end of this evening, that it is possible in the fairly near future, what we're doing at the NIF, as the National Ignition Facility is called, can be a part of your future, a clean energy future. And we want to demonstrate the route to fusion energy. And fusion energy is so cool is because, as Stuart said, not only does it power the stars, but we use the hydrogen in water. There's lots of it. And it has an energy density about 7 million times that of normal chemical bonds. That's nice. And also, no carbon, right? You're burning hydrogen. So we'll be talking about that. Not all of you can come out, but we do have public affairs tours, and Linda Seaver is here from the lab. And it is possible to come out to the lab if you make arrangements and to see it. And this is an interesting picture. I'll show you how it used to look 40 years ago in a second. But this is where the NIF is. It's 60 kilometers away. And it's out in Livermore. It used to be out ranch land, but slowly but surely we've been swallowed by San Francisco. Okay, so since I'm at the Long Now Foundation, I've been thinking about recasting history. So this is the history of the universe and the future of the universe. And the history of the universe goes back approximately 14 billion years, which is a long time. So if we look back in time on this log scale, of 10 years ago, 100 years ago, 1,000 years ago, 10,000, etc., you can see work our way back to 10 billion, 14 billion years ago, the time of the Big Bang. And then we can look forward. The Long Now view of the world is, can we look forward 10,000 years? Now, there's another way to date these things, which is 2020, 2110, 3110, 12,110 when you think about this. Or go back 10,000 years to minus 8,000, which is a little bit before BC. And you can see, because as a log scale, things get crunched up. But I think it's sort of an important point. What we're looking forward is 10,000 years. Can we imagine that? Think about what our ancestors who were coming into agriculture and forming the first villages and cities could possibly think about us today. Now, that's I think, the dynamic of the challenge that we think about when we think about our responsibility for the future. So here are the 4 stages of the universe from the human-centric point of view. There was this 10 billion years of pre-Earth, right? And about 5 billion years ago, there was a supernova around this part of the Milky Way. It blew up, put stardust everywhere, which we are now made of, right? And the Earth was made out of. And then we had Earth, and almost immediately there was life on Earth. And then we had the life on Earth stage, which is still going on. But before us, we sort of had about 4 billion years of life without us. And then we have this 100,000 years or so of human civilization. Human civilization I define as when we came out of Africa, right? Homo sapiens was established. We started roaming the Earth. And now we're looking at the long now vision. Now, what happened during these times? We had this very nice period of around 4 billion years where there was hydrocarbon and oxygen production. So all the critters that came before us were hard at work, making hydrocarbons, CH bonds, which we're now thinking about very carefully, and making oxygen so we could breathe. And at times there was a lot of oxygen, and when that happened, there was explosions of carbon making. And when there was not, there wasn't so much, but that was that period. What is this period about? Human civilization is hydrocarbon and oxygen burning. So we did that for a few billion years. We came around, now we started to harvest that. And what this leads to now, the situation that this precipice we're on, environmental disaster because of this burning, or do we find a way to have a clean energy future? So that's the history of the universe is in 4 steps. There wasn't the Earth. There was. We made hydrocarbons and oxygen. Then we started burning it. Now we're here today. What are we going to do? This is the problem. If you look only back 10,000 years, everything seemed fine, until the last couple of 100 years, right? Where the population of the Earth made this incredible change in slope. And it made this change in slope because of carbon, right? The Industrial Revolution happened, right? And actually, so you can think about it as James Watt, then Louis Pasteur came around and figured out health care. Then those are things like that, a few great men and a few great women who did great things. But they led to us learning to procreate. There was the Green Revolution. And go from, hundreds of millions to billions in a couple of 100 years. And this has changed things dramatically. In fact, if you just look at the United States, these are quadrillion BTUs. If you don't know what they are, it's okay. It's just a measure of how much energy we use. From the 1850s to today, we've gone from barely using energy to 3 trillion watts. Now, go over 3 trillion watts. For those of you who are mathematically, I'm supposed to stay in the light, so I'll move back here. 3 trillion watts, that's 3 times 10 to the 12th watts, right? And there's 3 times 10 to the 8th of us. That's 10,000 watts each. So all of us are using 100-watt light bulbs all the time. That's not including eating. That's the energy that we are consuming as Americans right now. And how do we do this? Again, go back 150 years. Remember, we are the carbon burners, right? So, 150 years ago, we were basically a wood society. But after a while, we would chop down the forest. We went over to coal, right? And then we went to oil, and then we went to gas, and then we finally did a little dam building and collecting hydro energy, and then we did nuclear, and then you see this incredible little renewables, right? Right. And I think this is a really interesting chart, and I want to show you some things about it that will be useful to understand our future. Because if the past is prologue, this tells you something. It takes a long time to change energy modalities. It takes about 50 years for coal to displace wood, and it sort of took that amount of time for oil to displace coal, but you see it didn't displace all of it. And then it took another 40 years for natural gas to displace some of the oil. It didn't displace any of the coal, though. And then we had nuclear sort of displace some of the gas, but none of the oil or the coal, right? So what happens is you have these modalities last for a long time, and they increasingly get harder and harder to displace previous types of energy burning. And the reason that is because you spend all that money to build that, and they generally last 50 to 70 years, and once you've done that, you don't want to throw it out. And in fact, your ratepayers, whoever you were during that time, say, no, I'm happy with this, I spent my money, let's use it. This is really the amazing part. In 1900, we were a 98% carbon-burning society, and today, 100 years later, we've gone all the way to 90%. So if anyone thinks we're not a carbon-burning society, and sort of really entrenched in it, look at this. We know that our energy supply is this is what we're doing, this is, a gas flame out, right? And what we have here is the following thing that we have to look at. What is the problem with fossil fuels? Well, going back, those billion or 2 billion years, we're burning up about 10 million years of hydrocarbons every year. Some people say 20 million. It's sort of hard to measure. And that means it's not going to last forever. So we might have 100 years to go of coal, 40 years to go of oil. These things are argued, but it's not 200 or 300. This is sort of where we are. Right? So it's not going to last forever. Maybe that's good. Fossil fuel can affect the quality of our life. This is a famous picture, of the bird's nest in Peking on a clear day, right? Right. This is old pollution, old LA pollution. And fossil fuel can lead to environmental disaster. Everyone knows this picture. And what I think is amazing about this picture, what's going on in the Gulf of Mexico, there's a 30-inch hole in the about a mile down in the Gulf that's putting out around something like 50,000 barrels a day, which is 1 million barrels, every 3 weeks or so. Sounds like a huge number, right? But just remember, the United States is burning 1 million barrels of oil an hour, right? So you think of that, right? And then you think about what's really going on in our world. This focuses our attention. It has taken President Obama's whole agenda off the table, right? This is where he's at right now. And that shows the instability of the system that we're living in. And the other thing that fossil fuels can do, it can affect the climate. Now, this is argued by some that it isn't exactly affecting the climate yet, or maybe have some smaller effect or unknown effect, or how it will develop over the next 50 years. But I think the preponderance of scientists sort of have taken the point of view that it is very likely that this is an effect that is real, and over the next 10 years it'll be sorted out. And science is slow in coming to conclusions, usually, and it's deliberate. I think this debate has been going on for a while, but I think it's obvious what's happening. Now, I don't mean Katrina was caused by global climate warming, but there are many things that are. And the way I think about it, and I know many of you have probably had this thoughts many times, for the first time, humankind is acting as a force of nature, right? And I don't mean that we're doing agriculture or things like that, or dragging, species around the globe in ways that are unnatural. Right now, we're in a place where we're acting like a force of nature globally. And this is, I think, something that's kind of a first. We've always been a locally driven species. So what one group of people were doing and what another group of people were doing was not affecting everyone. They could be localized, and now I like to say, we're not in a global society. We're in a non-local society, which has a slight subtle difference to me. We can think we're acting locally, and remember, all politics is local, but we're having effects on each other. And when you look at this picture, some people look at Greenland, and they say, that's a big ice sheet. Seems to be melting faster than people thought, right? The ocean seems to be rising. The amount of carbon dioxide in the atmosphere is going up. What the temperature is doing or not doing is really hard to tell on short time periods, but over long time periods is going up. And how is this going to affect us? Well, let's go back to the U.S. If you go back to the U.S., the way it's going to affect us, it's really hard to get out of this carbon habit. Because in 1970 or so, you can see everything frozen. right? So we were sort of 95, 90% carbon then, and that's where we are now. And those modalities take forever to change. So what do you think we're going to do? This is the fingerprint of the humankind, right? How it's dealing with us. This is the Earth at night. I think what's interesting about the Earth at night is how interesting you can see where we live, but it's also interesting it doesn't quantitatively tell you what's happening. China looks bright, India looks bright, but remember, they're using around 10% per capita energy that we are. And they don't like that. And why should they? They want to live at our standard of living, and they are raising their level of energy use rapidly. And there's going to be about 3 billion more people, sailing on this earth with us, and the amount of energy we need is going to go up. Now, whether it's 2 billion or 4 billion, which is also arguable, we're 6.5 billion right now. Some people go to 8.5 people, 10. I don't know what it is. It's a lot. Remember, China is sort of a billion two. If it's 2.5 billion, it's 2 Chinas. Right? It's 3.5 billion, 3 Chinas. It's a lot of people, and they're happening to us pretty quickly. So we are at a tipping point on where we're going. The climate's changing. We're running out of carbon. It's affecting the way we live. What are we going to do? This is something else that's happening. If you look at the United States only, we're now, remember we stopped building in the 70s and 80s, we have 70-year infrastructure. It's going to turn off or run out by 2050, 2060. And while it's going off, the electricity demand is going to go up. It's going up for 2 reasons. Even with conservation and even with efficiency, we are becoming a more electrical society. And we're using more electricity. So that combination shows that the demand is growing for electricity and our electrical infrastructure is going away. So there's this big gap that's forming, and this gap is kind of interesting. And if you look at this, you can see that we need around 250 gigawatts by 2050. So does everybody know what a gigawatt is? So a nuclear reactor is a gigawatt. Moss Landing, everyone knows on the way down to the aquarium, 500 megawatts. So the United States needs, but you can't build Moss Landing, that's gas. The United States needs something like 200 or so Diablo Canyons by 2050, or some other green source of energy. And it gets worse and worse after that. So 2030, 2050 is where things happen, and that's our challenge. If you look at the Earth, worldwide, not to beat this to death, it sort of gets worse. Now I show this in billions of barrels of oil equivalent. I show you these units so you just, when you're working and walking around, you see this. Here's where we are today. It's a fossil fuel society. This is what we think we have to do. Most models agree, not exactly, in order to stay at 2 degrees centigrade, which people forget is 4 degrees Fahrenheit on average above where we are today. And as a scientist, I just have to say, or as a social scientist, if I were one, turning that around, based on our history, is an incredibly difficult task. In fact, if you look at this says by 2050, 60, we should go back to pre-industrial revolution carbon emissions. How do you do it? It's real hard. So not only that, we have to make a huge amount of low carbon energy in the end of the century. And this is all going to happen in 2030 to 2050, only 20 years from now. The problem is, we talked about that lag time or inertia in the system. If we decide good ideas today, it's going to be hard to pull this off. One more thing that makes this even more difficult. We are concentrating into cities. Right now, this is the megacity look in 2000. Megacities are cities above a population of 10 million. This is how people think it's going to look in 25, right? There. You can see it, it's exploding cities. Why do people go to cities? That's where the jobs are. That's where culture is. That's where centers of power are. And by the way, they're more energy efficient. Cities are the most energy efficient parts of our society. This is where people are going. And Because they're in cities, they need base load power. We don't want to have power that goes on and off, based on whether the wind is blowing or the sun is out. We live in a 24-hour society. So we need energy that's affordable, clean, non-geopolitical. That's a big deal. We don't like depending on other people. No one likes depending on other people for where they get their energy. We'd like it to be inexhaustible. We'd like it to be non-proliferant, fit into a physical infrastructure that we have, right? That means you want to be able to plug into where you are, compact and acceptable to all culture, and deliverable and timely. That's quite a list, And most people, when they look at that list, say, well, I don't know what to do. Or everyone has their own idea what to do, and everyone becomes sort of zealots about their particular idea. China worked on population control and sort of helped on some levels. Some people say people shouldn't develop. They should live in a less developed society. Other people say we should renewables like wind or sun or sawgrass. Or we have nuclear, or we have carbon sequestration, take the carbon out of our carbon-producing plants, or we could be more energy efficient. All of these are clearly a part of our infrastructure, of our future, but none of them is a panacea. At least most people don't think so. So then I ask you, what did I come here? Is there another idea, right? One that could be really exciting. And the answer is, and I love this picture, it's a picture of the sun. What I love more about it is the picture of the U.S. space station flying across the sun. Because I think it sort of says man's capabilities for good or maybe you think it's a little bit too much, but it shows, we're not limited in our vision if we choose to. And I think the answer is right in front of us. Just look at where we are. Look at the sun. In fact, look anywhere in the universe, in our cosmos, and you come up to, and this is this beautiful picture out of the Hubble, and we're looking from hundreds of thousands to billions of years away in this picture, billions of light years away, and you say that fusion powers the cosmos. So every bit of light that you see in the day sky or the night sky, every bit is coming from burning plasmas, right, or fusion systems. And the question is, where did that come from? And that's, old Albert. So Albert in 1905, which was an important year for many things, besides this, the airplane appeared, right? The Wright brothers were there, Henry Ford was there. This was like an incredibly productive time for humankind. Told us that the way this all works, actually he didn't quite tell us, but he pointed the way, is that the reason that these things, this energy is happening is you can take mass, stuff, and turn it into energy. In fact, he even said more. He said they're the same thing, just how can you convert them from one to the other, and they're measured the same. And what's great about this is c, the speed of light, right? Is such a big number. So when you multiply c by c, you get a really big number, as we say scientifically. And so a very small amount of mass can be a very large amount of energy, if you can pull it off. Now, it's hard. And we asked, could we build a miniature sun on the Earth? And when I talk about miniature, you'll see I'm talking about the diameter of a hair. I'm not talking about a big sun. One of the reasons we like the sun is because it's far away, right? If it were close as Venus is to the sun, it's sort of a warm day, right? And if it's where Mars is, it's sort of cold. So we're sort of in that, Goldilocks planet, not too hot and not too cold, right? Just right. And that is actually true. And so could we do this? Could we build a miniature sun on the Earth? And so what's the recipe, in the cookbook, right? In the NIF cookbook for fusion on Earth. So we have to take hydrogen from water. Actually, you just take water and you filter out the heavy water. So at the time of the Big Bang, actually about 1 minute after the Big Bang, hydrogen appeared in the universe. And, and there was two types of hydrogen, regular hydrogen and which we call hydrogen, and the other kind, which is deuterium. And there's about 1 in 7,000 water molecules when you go out to the bay is heavy water. And if we filter out the heavy water and we place it in an oven and we heat it to around 200 million degrees Fahrenheit, for a few billionths of a second, you can turn mass into copious amounts of energy, and it has no carbon and no waste, right? So that's the recipe. So where do you get one of those ovens? Right. So there it is. That's what the National Ignition Facility is. It holds an oven inside. And to explain how we got here, we only have to go back 50 years. And this is, again, a California Bay Area story, which is kind of interesting to me. Charlie Towns, who's still at Cal Berkeley, he's 94 and still active in the field, invented or pointed the way, theoretically, to the idea of lasers. And he did that in around 58. It's a famous paper. But I think more interesting is Ted Maiman. Ted Maiman down in Malibu was working at Hughes Aircraft, where I worked at one time, and he showed the first laser. And I have actually held this laser, and it's and within the last 2 weeks, it's the 50th anniversary of the invention of the laser. And it's so elegant, you can't believe it. If you look at that sucker, it's so small, and it was so revolutionary. It's revolutionary at the scale of the transistor. People still haven't understood that, but in the next 20 or 30 years, it'll be clear that manipulating light using lasers will have more power, or at least as much power, as manipulating electrons using semiconductors. This is a powerful device, and there's where it started. And what's really amazing, this was on May 16th, 1960 at around 3 in the afternoon, at the lab, Livermore lab, 3 days later, and look at Livermore then, right? Remember that picture I showed you then? It used to be a naval base during World War II, and you can still see the runway. At that time, John Knuckles, who was working in the nuclear weapons program at the time, realized that that laser was the way to get fusion energy. And it started off a 50-year journey that we are coming to a conclusion of right now. So this is what he told us to do. Here's the oven. I'm going to tell you how big it is in a second. We have this gold can, and we have this little ball, and this little ball has a little hydrogen in it, and there it is. And it has a capsule wall that's about, I will keep using this, a little thicker than your hair, that's made out of plastic. That's rocket fuel. And what happens is, what we do is put laser light into this oven, right? And you can see the billionths of a second going on. And this oven gets really hot. And instead of baking it red hot like your oven does, it bakes with X-rays. And it absorbed on this little cake here and explodes and drives the hydrogen together till it's hotter and denser than the center of the sun, and it burns. And when it burns, you actually, if you went in there and weighed that afterwards, which you can't, but if you did, compared to beforehand, you would see there was a little mass missing. And that mass is turned into energy for us to harvest. So how big do you think that is? Anyone want to take a guess? That big. So that's the oven. In fact, I have one right here. I don't know if you can see it. Right? So that's it. This is that little gold splash there. That's the full size. And that little red ball, which unless you have Superman eyes, you can't see, is the size of the burning capsule, right? So that's a remarkable idea. That's the oven. That's the Betty Crocker, John Knuckles oven that we have to build. Of course, we got to build the laser. So we went off in the search of lasers, and from the 70s to the 80s, we built lasers that went from 100 joules, a joule is a measure of energy, to a kilojoule up by a factor of 10, to another factor of 10, to another factor of 10. Now we're up another factor of 100. And we're at the National Ignition Facility. That, according to everything we know, should be possible to get this burn to happen for the first time. First time in the course of human history, we will have controlled thermonuclear burn, changing mass to energy at a scale that's just right for making energy for our future. Now, it does other things too, and I'll talk about those in a second. So, it takes a long time to get, everyone together on doing this because it's a very expensive facility. The politicians show up and That's Miss Tauscher, who's, was our representative, and now she's the Undersecretary of State for President Obama. And there was our groundbreaking. And then, that afternoon, the real people came by. That's the real groundbreaking. And then, we had the barn raising, right? So that's when the NIF was coming together. And this is how it looked inside before we put the lasers in. And you can see these normal-size liver morons up here, right? Just so you can get the scale of this. And then it looks like that today, right? And it's kind of a great place to be for. And Stuart talked to you about it when you're in it. And I've been in it a few thousand times. I'm still amazed by it, because it's a masterpiece of American innovation, ingenuity, engineering, and everything that goes with it besides physics. And this allows us to do what we want to do. And if you look at it from above, you can see the humans. That's the scale of it right now, okay? And each one of those pipes has laser light in it, and every single one of them has the highest energy laser in the world. So every one of them is higher energy than any other laser, and there's 192 of them. That's why it's so cool. And by the way, this is the target chamber that we have that little target in, and I'll show you that. And this is when it was being put in place. It's 10 meters in diameter, or 35 feet or so for you of the English persuasion, and it's pure aluminum, and this is how the building looked before we put it in, and then we slid it in carefully, and that's how it looks today, almost. So I want to just show you this, without going out of my light. These are humans, again, and down here, so you can see the scale of it. So we had that little target, right? We have this big ball, and that's because it puts out a lot of energy, and we want to collect it nicely, and we want to have some optical elements in there that take care of this. But it's big on one scale, but I'll show you on another scale, it's kind of small compared to what it does. So that's how it looks. It actually doesn't look this way. This is the wonders of Photoshop. There's really floors here. Those people aren't floating. And, we just took them out so you could see the whole thing at once. That's how it looks like on the inside. So there's two things I like about this picture. First of all, how interesting the picture is with giving you a scale of this. More important, this is why people work for National Geographic. If you notice, this whole picture is in focus. And when the photographer from National Geographic came, it was a lens you could not believe, and it's kind of interesting in its own right. Okay, that's the target. Remember the target? So that's kind of interesting. That big thing, we have this little target. Keep this in your mind's eye, right? That's how big the target is. So we have to hit that target within, again, half the diameter of your hair. And we do it all the time. So we can point at that target. And, so now when you come to the NIF, this is what you see. It's a nice building. It's on 5 hectares or 12 acres. And it took 10 years to build it, and it should run for the next 30 years and should do great things for our country. If you take off the roof, I love this picture, right? And look at the CAD drawing, you can see, remember, if we talked about that laser bay here that we were looking at, or I can't see it, so I'll just stand here. The target chamber is here, right? That's how it looks. So what are we going to do with this thing? Let me show you how this works. This is the real control room. Let's see how we do it.
On my mark. 3, 2, 1, mark. Clock is running.
That's Glenn Hermes.
5.
He's shot the laser
4,
a few times.
3.
And now
2.
we're going
1.
over to a cartoon. So that's the electricity. Could we bring it down a tiny bit? Okay, that's fine. And this is the master oscillator room where it all starts out. It starts out at 1/1000,000 of a billionth of the energy you have before you get to the end. And it goes out into the laser bays that you saw, and it goes up in its preamplifiers, and it goes up to 1 billion times. That's where it started. And now you see you have this chunk of light that's around 20 feet long. And just remember, a nanosecond, 1/1000,000 of a second is how long it takes light to travel a foot. Right? So that if you took a movie of this is actually how it would look. The thing that was so hard about NIF was getting it to play music. Okay, so this is the Lego block of NIF, 8 beams, right? Now watch what happens. Now we have 48 beams, So that's its cousins coming along, right? Now we'll see another group of the family, 96 beams. This is in a 10-story high building. All these beams have to get to the target at the same time, and you can see they don't look like it, but watch. Boom. And now we turn them from red to ultraviolet, and they go on to the target. And you know the drill now, right? That little target gets real hot. And this happens in billions of a second. Billions and billions. Anyway, of a second. And when it's getting hot, it's making an X-ray oven. It's going to drive that target, to less than the diameter of your hair, hotter than the sun, higher pressures. And when it does, Albert Einstein appears and says, would you turn that mass into energy? And you got it. Can you use it? And we do. Yeah. I would take full credit for this if I had anything to do with it, but okay. So let me just tell you, this is a real picture, except this is a 1/10 of an inch. This is a big 1/10 of an inch. That's how big that peppercorn is when it starts. And I want to show you what happens, graphically, 10 billionths of a second later. Okay. So that's actually a picture, again, except it's the diameter of your hair, smashing this thing together, right? So when we've done experiments, and we're getting pretty far on this. And when you do stuff like this, you publish. You have things in scientific journals, and then we got the Rolling Stone of our life is the the Bulletin of the American Physical Society. So we got on the cover of the Rolling Stone, and there's a lot of attention being paid to where we're going right now. So this is kind of exciting. So NIF fusion is in the news, as you heard a little bit before. And I have to say, though, this is not a single laboratory activity. It's not a single discipline activity. It's multidiscipline, multi-laboratories, academia, industry, and the international community are playing a big role. In fact, 49 out of the 50 states, I'm really sorry North Dakota didn't play, but the reason is the company in North Dakota is a woman-owned company, and she moved to South Dakota. So we had North Dakota, and didn't have South Dakota, then we ended up with South Dakota, but not North Dakota. Okay, so there's 3,000 vendor partners, and we have international partners all over the world. So this is an international effort. And it's been flying under the radar screen. Most people don't know about it for a long time. And then we had dedication. And I got to say this, when you're doing big projects, and the NIF cost around $3.5 billion to put together, and it took 12 years to do it, you don't do that on your own either, technically or industrially, but it's a political and a social event. And, our California representatives, the Senator Boxer and Feinstein, the governor, Mrs. Tauscher, Mrs. O'Loughlin, the whole crowd played a huge role in making this happen. It was really a California event, but it was also a national event. And this is the kind of dedication that we had to making this happen, and this dedication showed how people were proud of it. But then something really important happened. Secretary Chu, formerly known to us as Steve, right? He's by the way, he got his Nobel Prize in laser research. Has been on a journey with us through the NIF. And he started out kind of skeptical, really, because he's a brilliant scientist who's used to tabletop work, very high precision work. And he really didn't relate to the NIF in the beginning. But over the last 5 years, he's understood where it is and it's important. And he came to the lab and he said, the NIF is a marvel, and believes the NIF will achieve ignition. Ignition is getting that burn to happen. And we should think about what we should do. And he said we should start planning for its success and what comes after it. And when he's talking about that is the energy mission. So the question is fusion energy a part of the solution to this problem, the global challenge, which I think is the existential and fundamental challenge that we face. Remember, we have to build the equivalent of, to do this as a species in the 30s, 40s, and 50s, 20 gigawatts a week. Now, 20 gigawatts a week is a big number, right? That means you do sort of the United States as we understand it in 6 months. And we have to keep doing that. This is a tremendous technical challenge, fiscal challenge, and also social challenge. So let me talk about what our idea called laser inertial fusion energy, which is to build the laser inertial fusion engine. What does the NIF do? The NIF turns laser light into X-rays, which drives that target, and that fusion happens, and then we get more energy out than we put in. That's kind of a nice idea. You have gain, energy gain. Doesn't break any rules of physics because you're changing mass to energy, right? And you get energy out, and now you collect that energy, and you turn it into heat, and you take that heat and run it past the heat exchanger and boil water or something like that, make steam and turn a turbine and get a generator and get electricity, and then you plug into the wall. So you start out with the highest technology, but you always end up back, with James Watt. Except it isn't a steam engine, it's this very fancy steam engine. So what we have to do, if we're going to do this, is we have to add something that converts that thermal energy, fusion energy, to thermal energy to electricity. So you can see this concept, if you just use the NIF and put that inside the system, you could do that, and then what we do is turn laser light into electrons, and the electrons go through the wires, everybody's normal wires, it's nothing different about the infrastructure, and when you do that, you could change the world if you could pull that off. There's one problem. We have to do it not once every few hours, but 10 times a second. That's the issue. It's a little bit different from an engineering point of view than what NIF is, which is an R&D facility. 10 times a second sounds like a big number, but if you multiply by 60, that's 600 RPM. So your car is going at, idling at 600 RPM, so it probably drives at 2,000 RPM. It's not a big number, but some people are a little bit put off by that thought, but if you go to your high-speed copy machines and stuff like that, they do that. That's not really our issue. This is how it would work. This is super slow motion. We fire in a target, literally on an air gun or something like that, and the laser light hits it, and we get ignition, and now we get out our fusion energy, and we have this salt blanket. Salts are good, not if you have high blood pressure, but salts are good generally, because neutrons have no charge, right? So they sort of tend to go through things. They don't interact with, atoms too much. They just tend to go through. They have to sort of find nuclei to bash into and slow down. But with certain salts, they have sort of these absorptions, and they really slow them down quickly. So if we have about 2 feet thick of salt, it'll collect the neutrons, and it'll get hot, and the salt will be molten. And, at temperatures like 600 degrees centigrade, so 1,000 degrees Fahrenheit or so. And now you have this perfect heat exchange medium. So it's a great medium for collecting them, and for collecting the neutrons, but now it's a great medium for heat exchange, so you could run a generator. And that's what we do, so that's how it works. But it sort of looks like this in real life. And you can see the salt flowing by. It actually flows pretty slowly. I just want you to know that's a gigawatt engine. So that, it looks big on one scale, but this is the scale of the NIF, right? And it's a 1.4 million. Just to say a gigawatt is 1.4 million horsepower, except it has no carbon. You're not burning carbon, and there's no CO2. And what are you using? Water. The hydrogen from water. And in fact, 1 liter of heavy water, so that pitcher, is equivalent to 2 million gallons of gasoline. It's a phenomenal thought. That's why we love hydrogen. Now, this isn't like hydrogen in your car, right? Hydrogen cars, this is very different. That's a chemical hydrogen process. In fact, when I first briefed the governor about this, he said, Ed, and I wish I could do his accent, but I can't. He said, Ed, what's the difference between your hydrogen and my hydrogen? Right. And I said, well, Governor, you could take your Hummer and drive it, your hydrogen-powered Hummer, and drive it from San Francisco to LA. I could take 7 million of them and drive them that distance. So it's sort of a really different scale. So just keep that picture in your mind's eye. In fact, think about the alternative. If you had, well, it's hard to think of a 1.4 million horsepower engine, but life avoids around 7 million tons of CO2 per gigawatt year, or 1,000 megawatt year. So how big is San Francisco since we live here, right? It's a 1,000 megawatt city, sort of. It's a little bit smaller. That's what we're burning. So 7 million tons of CO2 per year. So this is a very large number. So what is nice about this, laser inertial fusion energy is a separable system. That means that the laser that targets the fusion engine and the balance of plant, where we make electricity and ship it out, can sort of all be developed pretty much independently of each other. And what's really nice about that is that the balance of plant sort of exists. We don't have to reinvent that. It's everywhere you go, right? The fusion chamber has some material issues, but they seem manageable. The laser, people always bring up, and the targets have to be cheap. So that's the challenge, and I'll talk about that in a second. Okay. That's a 50 hertz laser, 50 kilowatts, burning through a ½ inch of steel. And that hole is this big, right? So when people say you can't make a laser do this, that's not exactly right. We just showed that. The question is, can you make it economically, right? That's really the question. This is a this will be a semiconductor-driven laser, and I'm going to show you something which you're going to have a hard time seeing, but this is, can anyone see this? Right, this is a laser bar that would be used to drive this. And if you looked at it carefully, you would, and you're from Silicon Valley, you would go, I know how to make that. Right? This is the kind of technologies we'll be able to use. And what's good about that is we get to ride on the backs of other technologies and make this happen. This is a target. That's a kind of a fancy-looking target. Remember, that's a centimeter. It's less than a ½ inch. And the question is, it's an R&D target. Could you make those cheap? And we want to make them for under 50 cents, right? And so we think we can. Here's our goal. Our goal is 25 cents or so. And for California, we would need about $5 billion a year. Sounds like a big number, right? And the tolerance on them is around 50 microns. Remember, your hair is about 100 microns or so. And there's a lot of things that humans make at billions a year. In fact, there's more than this list. Lego blocks, everyone uses those, are 2 billion a year. They're the most precision thing that you'll ever use in your normal life. And the reason that your kids can play with your Lego blocks is because they're so precise they don't wear, right? It's kind of an amazing thought. And they're free, and people say, what do you spend, what you spend for Lego blocks is to market them and ship them. To make them is essentially free, right? Except if you have to use oil to do it, right? Mil-spec bullets, this is an interesting number. There's like around 10 billion of those made every year. It's almost 2 for every one of us, right? And they have specs that are around, they're similar to what we're looking at, and they're bigger and heavier and have more material, and they're made for about 20 cents. And I also think if you look at soda cans, which is big, but they're made for a penny or so. So the whole idea of making billions of things at these costs is very possible, and there's all kinds of developments in nanotechnologies and the like that are going to drive this down, right? So here's our roadmap for life. We want to get ignition in quote-unquote 2010. We say 2010 to 2012. I'm rounding. This is when we think we'll be in a situation that will show that we can get more energy out than we put in. It's going to be an exciting day when that happens, right? We think in the 2020 time period, if there's a will, and I'm going to talk about that, we have the way to build an engineering demo so that people in the utilities and others could judge whether this is a part of our collective energy future. a carbon-free energy future, we think economical one, that's based on technologies that will inevitably get better over time, because they're technologies we're doing. And if that were true, we think in the 2030 to 2050 period, we could become a major part of the global energy society, which is the time that you saw that challenge arises. Can we get into it? Can we get to be a part of the low carbon future? So, where are we? We've talked to serious people. We're a bunch of brainiacs at the lab, and we're trying to reach out to people who can judge these things better than we can. So we've talked to the CEOs, vice president level of many utilities like Pinnacle West, PG&E, Mid-America, Nuclear Management, Constellation, Dominion, and Southern Cal Edison didn't get on this, Exelon. These have about 65% of the ratepayers in the country. And they're kind of excited about it. In fact, if you can get a CEO to come out for a day, in fact, a couple of them have come out for more than a day to hear about this and talk about it, it's a sign that serious people with serious money and serious ideas in this are interested. There's a lot of other people who have come out too, from people like Bill Gates, you always have to drop names, but many other politicians and business people, and people like Stuart, who are environmentally driven, who are thinking about our future and how to make it play out. Because this is a challenge for all of us. But one of the things these people ask is, can you do it economically, right? Can you have market penetration at the time they need? Is it operable and maintainable? Is there a supply chain? Does it fit into the licensing structure and energy policy? We have stories for all these, not for tonight. What I want to talk about, though, is the economics. There's an interesting view graph. It's blank, but it sort of tells the story of how the world looks. If you're a ratepayer, this is what you care about. This is, dollars per kilowatt hour. This is a dime per kilowatt hour. You like that. A nickel you love, right? Up here, you're not so sure. But this is what banks and utilities like to understand. This is the capital intensities, the dollars per kilowatt of capacity. Now I could put this dollars per megawatt or gigawatt of capacity, which is the kind of plants people would, and then you would say this is $20 billion, $25 billion, right? If you were talking about dollars per gigawatt. So that's what people are thinking about. So I want to go put some numbers up. So I think these are important things to consider. People are a little bit surprised when I show these. That's photovoltaic solar, right, for usable capacity. It's kind of an amazing number. A gigawatt of that sort of costs $25 billion right now, right? Most people don't know that. This is a heavily subsidized, government-subsidized activity. That's why people can buy that. If they didn't have that, it'd be very hard. And remember, it's only on during the day, not at the night. And the reason it works at all is because there's all that base power that you're adding into when you can and subtracting from when you can't to do this. Offshore wind is an interesting idea. It's supposed to be on most of the time, but it's pretty expensive. It's really the reliability and maintainability issues of windmills that are 500 feet high in 500 feet of water. It's a pretty hard problem, from an engineering point of view. The other ones are light water reactors, that's nuclear, which is, from the point of view of cost, is really good, and from the point of view of carbon is great. But the trouble is it keeps inching up, it inches to the right, in terms of capital costs. So that's why President Obama has the loan guarantee program for utilities to build new nuclear. So it's a real hard problem. There's fossil fuels. The way you do it is carbon capture and sequestration. If you could drag the carbon out of the flues as it was coming out and put it back underground, liquefy it and pump it underground, you could do something, right? But it's volatile and it's not a well-developed issue, and it uses lots of water. So a lot of places cannot use it right now. But all of these can be part of our energy mix. The question is, what about life? Well, we've done a lot of studies about life, and it's kind of interesting. It sort of looks between fossil fuels and light water reactors and capital costs, and also in the cost of electricity. Now, you could say to me, you've never built anything, how do you know how much it costs? Right? Well, we built an IF, and we know how much that costs, and we know what these diodes are going to cost, because there's a lot of models for semiconductors, and we think we understand targets, and the building stuff we think we get. This is probably reasonably accurate, you know. The thing that's interesting about it is it's not a carbon producer at all. It avoids all carbon, and that's really an important issue, because if you look at what would happen if the United States deployed, you know, 700 of them, like we talked about in filling that wedge, which is not hard to do. You're talking about starting in 2030, doing like one a year and going up to 2040, one a month. You could sort of displace 140 gigatons of carbon dioxide compared to coal. By the way, those are called wedges. If any of you are in this world, that's a lot of wedges. There's 30 wedges on Earth, right? And you know, if this were more displaced, this was a part of our worldwide community. And again, this putting this in fits models for how plants are coming offline and how we could put them online. You could have a big story here. And remember, the cost of carbon is expected to be around $100 a ton, mitigating carbon or buying off carbon. So just to go over it, 140 billion tons is $14 trillion. So you could start paying for this on its own. It could pay its way into the future. And you know, that would change also a lot of stuff about how to do this. You know, if you think that's what the cost of carbon will be, which I think a lot of people do. In fact, if you look at how much would it cost to develop it, you know, if you assume $20 billion in R&D and development funding through 2030, so to build the first 2 plants, right, and you know, develop them and build them, and you discounted the value of that carbon dioxide, you're talking about $1 per ton. So this is an insurance policy that you would like to have. You know, you spend $1 to avoid $100 forever. It's a really interesting idea. So the RD&D costs, you know, over time are essentially zero. So let me just finish my talk. You know, laser inertial fusion energy. It's sustainable, it's carbon-free, it's not geopolitical, it's safe, it's modular, it's compact. You could do a relatively rapid development path. It uses our infrastructure. What's really cool about it, it will always accept evolutionary improvements in the semiconductor technology, performance of targets, and we don't have to invent our own industry to do it. We use other industries that already exist. This is sort of, you know, too good to be true. All of these things coming together. You know, we're about to find out how good it is to be true. You know, we think we have a story. We think it's well analyzed. We have a lot to do to make this all happen. But, you know, look what the choice is. You know, we are at a knothole in the energy environmental challenge, right? You know, I think the sweep of history from 100 years ago to 100 years from now is kind of an interesting thought. You know, I have to thank the Long Now Foundation for getting me to rethink how I think, right? And, you know, when I thought about this, what was 100 years ago? We had Einstein show up. You know, this was really the beginning of modern science as we know it. You know, we had quantum mechanics was developing. You know, everything we know about our post-industrial revolution age was changing. Literally, my grandparents were using horse and buggy, right? It's a fact when they were born. You know, this is when this period was changing. You know, in 1960, 50 years ago, you know, the quantum revolution was on, the integrated circuits were happening, the laser was developed, And here we are, in 2010 on the verge of proving that we can get ignition, gain, using hydrogen as a fuel with lasers. And what do we have to do? Do we have a future that's bright and clean 100 years from now or not? How do we get through here? This is sort of this knothole that we face. Now, it looks like it's in 2030, but it's really right this second, right? This is our challenge, and this is our responsibility. So, what's your role? So I didn't come here just to talk. I'm here recruiting and signing up. So, we have a clear societal need. And when I talk about societal need, I'm talking about, our responsibility as stewards of our own planet. And, there's several solutions. I don't want to come across that there's only one. But they have to be worked on. We have to look at the options. And scientists and technologists can give you a lot of choices. And I hope this is one that you will go home and talk about. But it won't get done because we did this, right? There are issues of policy, funding, industrial commitment, communication, personal commitment to our own future and our children's future and our grandchildren's future. But the problem is we live in a world that is, let me tell you, there's a brick wall here, and everyone knows it, right? Which is short-term vision, unwillingness to invest in what are obvious problems, vested interests that have different points of view, preconceptions about what can and can't work, sometimes called skepticism, and apathy. I think the amazing part of the Gulf of Mexico is, so far, nothing has happened. It's sort of scratching the back of your head, right? But it hasn't. We haven't woken up to it. And I also, again, remember, that's going at a very small rate compared to the amount of oil we're burning in the United States. I think that life, if we had a lot of friends of life, if they were talking to their politicians, if they were talking to each other, if they wanted to learn more about it, come to our website, lasers.llnl.gov, if they made a story, could make this happen. So we can't do it on our own. We need your help. And, we can't, if we do that, I think we can jump that wall, or if we're quantum mechanically thinking, tunnel through that wall and not even touch it, right? So when I look at this, is there fusion in our future? I love this picture because, that's 4 billion barrels of oil, 4 million barrels of oil coming out of the Gulf, right? When I show this to kids, I say, where do you see your energy future? And of course they see the tanker. And then I say, look real carefully. And it takes them a long time to see the sun. And then I say, what's burning in the sun? Water, right? So fusion is in our future. Can we make it happen? Let's invent the future together. Thank you for your time.
They're going to raise the screen. We can sit over here. Who's your competition? Have you been around to some of the other laser facilities? Not everybody's using other fusion facilities. Not everybody's using lasers.
Right. So there's, there's 3 types of fusion to first order on Earth, in the universe, right? There's gravitational fusion. That's when you look up in the sky, just gravity squashing together gases until they get real hot and burn. There's laser inertial fusion, which is where we, create that oven and smash them together. And there's something else called magnetic fusion. Magnetic fusion is a very different process in that it's not high density. It's very low density, but very hot. And you build a magnetic bottle, so this very hot gas never touches the walls of the chamber. Because if it did, first of all, it would cool and stop stop, the reaction would stop immediately. So this is a big community worldwide, and magnetic fusion energy is being demonstrated, hopefully in the 2025 to 2030 time period, at a facility called ITER, or ITER, or ITER, if you're in Cadarache, France, where it's being built. And right now, it's going through sort of a little bit of a rough period. You'll be reading about that in the near future. Their goal is to build this facility and have it operational in the mid to late 20s. So those are the possibilities. You know, we hope to show that capability in the next couple of years versus the next 20. So that's a slight difference.
There's outfits like, I think there's one in Vancouver that is trying to do a pulsed version of fusion.
Yeah, there's a company called General Fusion in Vancouver. It's a small private company. They have some ideas about how to do it. I was in Vancouver at Ted Maimon's, the inventor of the laser, his widow, Kathleen, had a sort of a party, the weekend of the 50th demonstration. And I met some of those people, and they're enthusiastic, I'll say that, but I think they have a lot of work to do.
One question here from Gordon would be clarifying for people, compare and contrast fusion and fission for energy purposes.
Okay, so, fusion, there's, if you look at the periodic table, right, you have one corner, you have the very little baby, atoms, which are hydrogen, right? And then on the other side, you have the big honker, like uranium. And uranium is a fissile material. And its nucleus is so big, it hardly stays together. Now, it actually stays together for billions of years, but it's sort of liquidous. And every once in a while, quantum mechanically, it comes apart. It fissions, splits, and you get energy out that way. If you put enough of it together and it's enriched, when it's fissions, you can take the neutrons that come out and hit some other ones like that and split them again, and you have that famous chain reaction. And if you build a fission power plant and you just keep it right at the edge, which is not hard to do, you can just keep energy coming out. Fusion is the opposite. We take, hydrogen atoms and smash them together for a very short time. So this one only lasts for trillionths of a second. I have to tell you, if you built a fusion power plant like Life, and it was running 10 times a second for a year, all of you should know there's pi times 10 to the 7th seconds in a year. Does everyone know that? About. So that's pi times 10 to the 8th shots, and it's on for 10 picoseconds. So that means the plant would actually be putting out energy for 3,000ths of a second per year. So it's never on. But you collect the energy in the salt, and that sort of keeps it, thermally constant. So that's the difference. One is a coming apart process. One's a going together process. One is cannot sustain itself. One can sustain itself.
So you're hoping for ignition this year or early next year, and then the roadmap says 10 years to the prototype of an actual fusion reactor that supplies electricity. Most of that 10 years will be spent doing what?
Okay, so, remember, this is if there's a will, there's a way, right? The beginning will be, convincing people this is the right thing to do. But there are several things you have to do. There's engineering issues and technical issues that have to be done, and facilitization of certain parts of the semiconductor industry and other associated industries, building partnerships to go ahead and do this and put it together. It ends up the scale of these projects, like the NIF, it's sort of 10 years, right, for the first one. Just 10 to 12, just the way it is. That's the inertia, that's the arc of starting, designing, building, commissioning, getting operational. Just the way these kind of projects run. Our goal is, once we get going, is that you could sort of turn one on in a very modular way in 2 years. Now that's sort of ambitious, but right now, if you order up a 500 megawatt natural gas generator, you can sort of turn it on in 2 years. And we think of building a laser factory and a target factory, and a parts factory, so that you just ship it in, on normal trucks and things like that.
Now, as I recall when I was visiting there, you said that this thing it scales up pretty well, but it probably doesn't scale down much below a 1 gigawatt reactor.
Yeah, I talked about that. Fusion likes to go big, right? And that, the way the energy works out, if you go from 1 gigawatt to 1.5 gigawatts, the cost of energy drops pretty nicely. So you can make it small, but you pay for it. But we have some new ideas that in fact, we're going to have a meeting about it actually tomorrow, I think at 10:30, to talk about some ideas that might make it much more modular than some of the ideas we have now. People sort of like, in some parts, 250 to 500 megawatts is sort of, chunkiness of systems right now. And they don't like much bigger than 1.5 gigawatts because it sort of distorts the grid, how the grids look like. So we're looking at, how we could scale it down and still maintain the cost.
Well, you've got a $3.5 billion 12-acre facility. Scaling down sounds like something you want to do.
Well, I actually want to talk about that. When you guys and gals buy energy, don't think that it doesn't cost billions of dollars to put in gigawatts, right? Because it does, and there's no doubt about that. That's what I was showing about that curve. You saw from $25 billion a gigawatt to $3 billion a gigawatt. This is an R&D facility. It's not a production facility. And a lot of things came along for that $3.5 billion. We revolutionized the glass and optics business of the world, certainly our country. We changed the nature of many aspects of control systems and database systems and many other things. So it really is a part of our national competitiveness. And the thing that's also important is that it's part of our strategic defense program and also our look at the universe. We're going to be able to do experiments where we can simulate what's going on in the stars, in supernovas, inside planets, right in the NIF. So it has a broad set of uses. So I think it was a good deal for $3.5 billion. But we worked hard to, we work for the taxpayers, and we are taxpayers, and we take that job very seriously.
Say more about the national defense aspect. I assume that this kind of money coming into an operation like this, particularly at Lawrence Livermore, is not going to be just about energy.
Correct. So, when the first President Bush stopped nuclear testing, right, which is now 19 years ago almost, there was a major debate about, well, how would you ensure the stockpile, our nuclear stockpile, would be safe, effective, and actually we would know how it worked over time because it ages. And people always use this example. If someone said, here's a plane and it's at the end of the runway and you can't start it, ever, and 20 years from now someone says, we'd like to see if it works, but we're going to check it by having you fly it. Would you get on it? Now, the goal here is not, of course, to use these weapons, but we do have a responsibility through treaties around the world as the deterrence, and protect the free world and much of it, with the assuredness that our stockpile works. So the NIF is a part of that capability. You have the ability to do conditions that exist, in the stockpile without testing. And President Obama has just actually spoken to this issue and reaffirmed how important this is.
Now, is our stockpile mostly fusion weapons or fission weapons, or does that bear relation to the research you're doing?
Well, I think you all should go to Wikipedia and read it. Our stockpile is a combination of fusion and fission weapons.
And so this lets you do research on the fusion aspect of that?
Yeah, and all aspects of it.
Fair enough. What do the astronomers want to do with your equipment?
Okay, so this is actually what I think is, to me, some of the most cool stuff. When you look up at the planets that we are finding right now. Remember, we were 9 planets, and then we were 8 planets. Poor Pluto, right? Right now, we're sort of 400 planets, and the Kepler Space Telescope is out there right now. And I know from some of my friends in Berkeley and other places that some very exciting announcements are coming out, probably this fall. And it's a very interesting thing. As we find more and more of these planets, we thought that we understood our solar system. But now our solar system looks very strange, right? And we can create the conditions that exist inside the Earth. Inside the Earth, the iron that we have on Earth does not look like the iron that it has inside the Earth because of the pressure it's under, or in Jupiter, or in Neptune, or in these supergiant Earth planets that are being found. And hopefully people, will use the NIF to unravel these secrets. We're also going to be doing supernova studies, little tiny ones. So instead of looking up in the sky and looking at something that happened a billion years ago, you could say, we'd like to build a tiny supernova, on April 28th, at 3 in the afternoon. Bring all your diagnostics. And not only that, we'd like to play with it. So on April 29th, we'd like to build a slightly different one and really just sort of unravel that physics. So this will be the first time we can do experimental astronomy, on Earth. It's kind of a great idea.
It's a sign of a good talk. We'll get lots of questions. Some of them are kind of technical, basically looking at what are the sort of limiting factors here. So one question from Max Ferretti is, how do you deal with radioactivity that results from fusion on a large scale? Do you have to wind up burying the chamber, or the targets once they've been used, or what's the issue with them, and so on?
Okay, so what happens when you ignite a target, you get neutrons that come out, and neutrons can interact with a lot of materials, and it's called activate them. So if certain materials absorb a neutron, they can become radioactive, and then they'll split, they'll fission, right, and give off, radioactivity. So that sort of could be a problem, in some senses. But what we do is we use materials that are generally resistant to that kind of activation problem. And there's a lot of special materials that have been invented for the nuclear industry and the fusion industry over the years, and there's tremendous work in it to bring that down to a very low level and make it short-lived. So there will be some, like in the first wall is the first place. Remember, you have to have those neutrons go through the first wall before they get to the salt. That wall can become slightly radioactive, with lifetimes of years, and you would just, at that time, use, it's called shallow ground storage, or open cast storage, and then after a few years, it would be returned to its normal condition.
So is that the extent of the radioactive waste stream basically coming out of these things?
That is our hope, and we're studying that quite a bit. Right, yeah, that's our goal. Remember, we're not putting in anything that has long lifetimes, and we're trying not to have anything nearby that could attain long lifetimes.
A couple of people were curious about, you mentioned gold in there. Is gold the limiting factor? It's an expensive material.
No, gold is just the limiting factor in keeping physicists happy. We use about, in one of those targets, that, right now we use about 100 milligrams of gold, so it sort of doesn't cost very much money. But in a real target where you're thinking about, as I said, billions per year, you would never use gold. You wouldn't use gold for a lot of reasons. First of all, it's expensive. It's hard to, use, and it's not very helpful because its melting point is high. So what would happen is you would blow this up, it would get really hot, and it would fly apart, and then it would condense in places that were cold and sort of form stalactites and stalagmites. You don't want that. So what we're thinking about a lot is sort of lead targets. Lead is almost as good as gold in performance, not exactly as good. It's a few % worse, but it has a very low melting point. Better yet, going back to that other question, it doesn't get radioactive, and you can keep using it over and over and over again.
There's a vast, the technological sublime aspect of visiting your scene is, besides the target chamber, which is pretty exotic in its own right, but the vast array of laser apparatus that's involved. Is that all is a given, or is there a way to make that more efficient somehow?
Yeah, NIF, you have to understand, no matter, even though it's the most, advanced laser on Earth, is sort of built on 1990s technology, right? Because it's that's the inertia in the system once you start designing it till you procure it and build it. So it goes back into the 90s. So we have ideas that will take that laser bay, that was almost 400 feet long, and put it into 30 feet, and have about 10 to 20 times more efficient use of electricity in turning electricity into light. And so our goal is that it's truckable, right? That you can put it on an 18-wheeler and drag it around. Not the whole thing, but each part. And actually, our goal for a gigawatt plant would be it'd be smaller than the NIF. Now, the NIF is, people say it's the biggest laser, but I always point out it's smaller than Costco, right? And compared to IKEA, it's somewhere in the bathroom section.
Question here from Roger Smith on when you get ignition, or if you get ignition, but we all say when. What's basically the efficiency of that event, the energy out versus energy in?
Okay, so there's our goal is, ignition is defined as the following. The formal scientific definition. When you get as much energy out as you put in, then you have a burning target. If you're a real physicist, right, when you get about 15% as much out as you put in, it's actually started to burn, right? But no one wants to have that argument, so they just say 1. Our goal in the first few years is to get 10 to 20 times more out than we put in.
Any sign of advances in the tea kettle aspect? You mentioned that we're still doing James Watt's steam engines here.
Well, yeah, actually, there are really, we make a joke, but, James Watt was, when he did his work, he was converting energy at less than 0.1%, and we're sort of looking at 50% right now, and people have ideas to get higher conversion efficiencies. But this is a thermodynamic problem, Mother Nature, everything is running downhill. Anytime you touch energy and change it to another form, you lose. You can't stop that. And so 50% is a good number. We talk about plans with 65%, but those I think are pretty far-fetched for the next 10 years. New materials will come by. That's how this field goes forward, that you can run them hotter, and the larger the temperature difference between the input and the output, the more energy efficiency you can get. So if you could run it hotter, we'll get more later.
Here's kind of a long now question from Stephen Hill. In 50 years, will we look at your life technology as being as crude as first generation nuclear? And do you have any sense of what second generation fusion might look like?
Well, my answer is I hope so, right? Right now you have to understand the targets we're using are sort of very conservative targets in the sense that, we have experience with them. We think we can calculate them with the kind of computers we have. We think we can understand their performance. And we're not pushing on that agenda very hard. We're just pushing to prove that you can do it. Like if the Wright brothers said, I'm not going to try to fly a plane until I have a jet engine, we would have waited a long time. At the same time, we have all kinds of ideas that have been around and are growing that show abilities, on paper, to get as much as 10 times more gain from targets that we have now. Certainly, the drivers will inevitably get better. They just can't help themselves. They, will with or without our help. And so we think that, in 50 years, this will look pretty crude. And by the way, if you look at the lasers we were building 20 years ago, they look really crude, right? So that's just going to happen.
Which raises the question, is 50 years of laser development at Lawrence Livermore, 50 more years of laser development. Are lasers proliferating, as you suggest, with transistors to be at the core of all sorts of things?
Lasers have. Lasers are so fundamental to all of your lives every day, every time you get on the phone, every time you turn on your DVD, every time you turn on your TV, all your cars are manufactured and cut and welded with lasers. Lasers are just so ubiquitous in your life that no one knows they're there. That's the transition they have made. And it's going to be, I've read, $1 trillion business by 2015. So it's a part of the world economy. And remember, photons are so good, right? They have no mass, they have no charge, but they carry energy and momentum. And by the way, they also can be coherent. So they're just too cool.
Hear, hear. Here's a question from Paul Hawken. How can you provide affordable clean energy when deuterium fusion reactors are neutronic and must be serviced by robots?
Say that again. I just missed it.
How can you produce affordable clean energy when deuterium fusion reactors are neutronic and must be serviced by robots?
Okay, so first of all, we're not doing deuterium systems. We're doing DT, but that's not deuterium tritium, right? Because that's not germane to your question. Your question is a good question. When you do this, it'll sort of run itself, and for years at a time. But at some point, you'll have to maintain them, not the laser, right? And not the final optics, and not the balance of plant. None of that stuff will have any radioactivity. But the target chamber wall will be, as I said, get slightly hot. So what you have to do is, move it out, and we have an idea about how to do this, which is put it on a railroad track inside the building, take it out, let it sit there for a little while, and then put a new one in. And a little while is depending on how much shielding you want to put around it for your robotics, or from hours to weeks. So this is not a big issue with respect to how long it takes. And also, this is kind of small. As I said, if that target chamber were 10 meters in diameter, like NIF, it's kind of a small item to maintain. And this is, of course, an engineering problem that we have to take on, and we take, there's a lot of experience in the world with this kind of robotic system.
Last question from Robin. What's the gating factor in fusion research now? Is it funding, understanding, infrastructure, or something else? In other words, what can most help to make this move along?
I really think this is a great question. I think that...
That's why it's the last question.
I think I sort of tried to say it. I think it's all of you, right? How do we feel about what we say about our environment and our economic future and what our children are going to deal with? And I think that this is a relatively high payoff, and with respect to the risk, incredible return on investment with respect to our future. And I think right now, when we look at it, is funding the demo plant, right? Presumably we get ignition in the next couple of years. It's going to be all over the newspapers. Everyone's going to be, talking about it, very excitedly. I always ask this question, is this Apollo 17?
Yeah.
Right? Some people think the Apollo program was a big success. I grew up, it changed my life. Some people say, well, what happened? Right? That's the moment we're going to reach. Are we going to have a future vision, and be able to jump on it? And that's because we're going to have mobilized our politicians, and we're going to have, word of mouth and grassroots efforts making this happen, or not? I think that's the big challenge, and that's why I'm here today.
So it sounds like the prototype is not the current building and apparatus you have. The prototype is a separate building, a separate apparatus, specifically not for research, but for energy, and it will cost some amount to make that prototype.
Well, I would say it in two ways. This is the performance prototype, which shows all the capability of the gain to show that the basic principles are correct, right? And it will show over years that you can do better and better. It will always be that research machine. But the one that, utilities have to then sign up for, you need one more step. And that's the one we're talking about.
So that would be...
That's the life demo, right?
In your view, that would be another facility you would build at Lawrence Livermore?
Actually, I don't get to decide where that's built, right? That will be a debate, of a lot of people of where's the best place to put it. I'd always love it to be in the Bay Area, but it's not my choice alone. That's, again, we'll decide together.
What are chances of it being somewhere outside the U.S.? Some other country saying, well, we're going to proceed now.
Okay, right now, we are the clear world leaders in every aspect of this activity. I traveled to China about a year ago, and I was with the deputy chief of the Chinese Academy of Sciences, and he was asked, they're building a NIF, also, Shangguang 4.
Where?
In Shandong province, right? and he was asking me how it was going, which is sort of kabuki because he knows how it's going. But anyway, but we sit there and I'm telling him and I said, and how's yours going? And he says, sometimes it's good to be second. And I take that, comment very seriously. I was just in Japan last week. The Japanese are interested maybe in partnering with us. And I hate to say it, 2 weeks ago or 3 weeks ago, I thought I lost track. I was in Europe and I was in Great Britain and France. This is attracting a lot of attention. And, it would break my heart if it were built for the first time somewhere else. And it's all my intention to make it a part of our national portfolio, and hopefully your intention also.
Well, that leads to one more question, because with nuclear, people are always saying, well, there's this weaponization capability, and we have to have these fuel banking workarounds and so on. If United Arab Emirates is going to have nuclear, then they should buy the fuel from somebody else and send it back to them. Suppose United Arab Emirates, it's just the kind of thing they might do. Abu Dhabi says, okay, we're going to have a fusion reactor. Do we care if there's any kind of weapons application?
The answer is, just to say this, is I'm not going to give my opinion. This is the opinion of the State Department, the Department of Energy, and others. Fusion is not considered a proliferation technology. If you wanted to break out to use this for weaponization or to make, fissile materials, and you thought this was the way, you would have failed the IQ test. This is, people are doing it without this trouble. So the answer is it's not considered a proliferation technology. I think the real issue is the one we talk. It's a national competitiveness issue. If Abu Dhabi or somebody else, were to try to buy this capability, or develop it on their own, I think it would be real hard for them. They don't have the infrastructure to do it. But I just would, again, this is our, we invented this. We've developed it. It's a part of this, I have to say it, it's a Bay Area story. Everywhere you look around the Bay Area, there's intellectual prowess, manufacturing prowess to pull this together. Investment prowess, venture, and the like. So I think this belongs here very much, and I hope that someday, hopefully while I'm alive, San Francisco is powered by fusion, and I hope 100 years from now, we've made the switch to a fusion society, which is unlimited energy, clean energy, so the next 10,000 years are kind of a nice 10,000 years.
Bring it on. Thank you.
Thank you.
Well done.
Thank you very much.